Hi, welcome to lecture 19. In this lecture, we're not going to study any new fundamental principles. We will be looking at an example of what we already know. This example is called the Attwood machine. And it's named after George Atwood, who was a mathematician in the 18th century. And I always find it funny that this thing is named after someone. Like here's what it looks like. So this is the device we're looking at. We have two pulleys, or maybe just one pulley, doesn't really matter too much. Then some weights you're going to hang from it, and the weights, one is heavier, one is a bit lighter. And you can kind of already visualize what's going to happen. This one's going to go down, this one's going to pull up, a bit like a sort of counterweight setup. And that's it. Like that is it. That is the thing that's called the Atwood machine. And it's rather peculiar that this particular setup has a name, whereas other setups with pulleys don't. George Atwood wasn't really known for much else. He was a mathematician, as I said. He was a fellow of the Royal Society, so he had some repute, I guess. But ask any physicist or mathematician nowadays, George Atwood, what do you know about him? At most, they're going to come up with the Atwood machine. So there's probably some history behind this that I'm not aware of. Anyway, it's a fantastic little example to study. Let's look at this again. So we have two masses, and two weights, right? Each weight, of course, has a mass. Weight is a force, but of course we also use weight to mean the object that is, heavy little thing here, right? So this weight, they're different. The string runs over a pulley. We're going to assume the string is light. That means we're going to ignore the mass of the string. Like the mass of the string itself is insignificant. It's very tiny compared to the mass of the weights. Also, we're going to ignore the mass of those two pulleys. And really, if we can't do that, if they're heavier, then we'd need to apply some rotational dynamics because it'll take some force or some so-called torque to get those things to spin in the first place. But because we assume those pulleys are light and they're frictionless, we can ignore that effect. So really just saying this one is pulling down this way, this one is pulling down this way. At least that's a kind of intuitive idea. Okay, so let's analyze this. Let's look at it in a bit more detail. So here's the sort of simplified setup. There are two masses called the big mass big M, the little mass little m, and we're going to assume that big M is bigger than little m. 2 kilograms, 1 kilogram, 5 kilograms, 3 kilograms. Whatever masses you want to pick, but this one's bigger than this one. Of course, if it had been the other way around, it doesn't change anything, right? I could have thrown this one on the other side. But we have to decide, okay, one's bigger than the other. We're going to assume that the system is initially at rest. So maybe you're holding it, like you're pinching it here, you're holding it, or you've clamped it somewhere. So it's not moving. And then we let go. And then, of course, we anticipate this one's going to move down, this one's going to move up. So questions. Does the tension change when we let go? What is the tension? And how fast will the weights move? Like how fast is one going down? How fast is this one going up? So to figure those out, let's draw a free body diagram, right? Actually, I'm just going to draw free body diagrams up here on this diagram. Now, it's very simple in this case. There isn't much going on. There aren't many forces. There is the weight down. Actually, let me not do that. Actually, no, let me do that. So the weight down. The weight is mg, of course, right? The weight. And then upwards, there's what is a normal force? No, it's not sitting on anything. It's not resting on anything. But there's a tension, right? The string is attached. So the mass is going to be a tension. And right now, I'm not going to make any assumption of how big the tension is compared to, say, the weight. I'm going to call this tension T. And I should have closed the parentheses there. Okay. So I'm not saying tension is greater, less than, or anything than the weight, right? I'm just drawing it because I know what direction it is in. Of course, this one here also has a weight. And the weight here is going to be a lot smaller because the mass is smaller. And it has a tension too. Now, is the tension in the string here the same as the tension here? Well, the string is light, which means that it doesn't take any sort of force to keep the string up, to hold the string. Like if this were a heavy chain, you probably imagine the tension up here would be higher than down here, because up here the chain link here would have to hold all the chain all the way down, and that itself has a certain amount of weight. The tension would definitely be different in that case in different parts of the string. However, because we assume the string is light, all the string is holding is the little mass down here. And because the pulleys are frictionless, again, means the tension here is the same as the tension here. If it was not, if the tension up here were, say, greater than the tension here, well then the tension here would pull the bits of string in the middle like this way over the pulley, and so the tension would equalize. Right? So the tension is the same, at least if nothing is holding the string. Right? This is after we've let go for sure. So I should draw this tension arrow here the same as this tension arrow here. Same T. A different weight, but same T. So, well, does the tension change when we let go? Well, yes, it must. Let's understand this. So let's answer this one first. Does the tension change? Well, to answer this, we only have to look at one of the masses. Let's take the heavy one. So before letting go, what do we have? We have 0a, 0 acceleration. So that implies that the tension is equal to mg. Right? So we have mg down and the equal tension up. After letting go, well, now we have some acceleration. We don't know what, we're going to figure that out, but it's definitely not 0. There's some acceleration. That means t is not equal to mg. I mean, if it goes down, we expect t to get smaller because mg has to be bigger, so there's a downward net force. Let me draw this. And mg, of course, doesn't change because the Earth doesn't care, always pulls with the same force on a particular object. How do we know that? Because we know there is a net force down. Right, so this means we separate those a bit there. So I hope this makes sense, right? Beforehand the force is balanced, that's when nothing is moving, but when you let go, you can see acceleration, and so that tells you that the forces are no longer balanced. And because mg doesn't change, that means the tension must have changed. So that implies that the tension changes. And beforehand, we know what it is, right? It's mg, before we let go. Afterwards, well, we're going to figure that out. There, okay. Let's keep our picture. I'm going to go to the next page. We're going to figure out now, our questions are, what is the tension in the string, and what is well, how fast will the weights move? So let's keep those questions in mind. Put this over here. Okay. So let's draw the free body diagram again, just so we have them on the top of the page. So for the one mass and for the other mass. For the first mass, the heavy one, we have mg down and a tension up, and we know the tension here will have to be less than the weight, because otherwise, well, it would not be starting to move down. And the other one will look something like this. Right, there's the heavy heavy, weight, lightweight. So the net force in this case, let's put F net for the heavy one, is going to be mg minus t, right? Mg down, that's of course downwards. So that means the acceleration of the heavy one is going to be the net force mg minus t, and divide by the mass of the thing, m, down. Now I'm not done. I don't know what the acceleration is because I don't know t yet. Right, so this is an incomplete solution so far. What I do know though, and perhaps I should have mentioned that first, and hopefully you understood that already, is the question asked us, how fast will the weights move? Now of course the answer is not going to be a speed, because we see, okay, the forces are not balanced, it's not going to change. We're not going to go down at a constant speed, we're going to go down at a constant acceleration. So that's what we're going to find. Right? I could have asked, or the question could have asked, what is the constant acceleration with which the weights move? But that's kind of anticipating a lot of understanding of the physics here, right? The fact that the acceleration is constant, well, is something we understand, not because the question tells us so, but because we understand Newton's laws, specifically Newton's first and second laws. Alright, so the acceleration of the heavy box is this, downwards. Now, let's look at the other one. The net force on the light one is going to be, well, it's going to be up, right, because the tension is bigger than the weight. And we know that because we sort of know, okay, it's going to move up. We also, I mean, I think that pretty much sums it up, I guess. It's the easiest way to talk about it. So what is it? So T minus mg up. Right? So I flip them, mg minus t, t minus mg, and because I know which way it's going to go, so I'm just going to state that explicitly, right? No need to get tangled up in minus signs. So that implies then that the acceleration of the light box is t minus mg divided by the mass, Newton's second law, right? And the second law says divide by m, so the m here is a little m, the mass of the light box, because that is the object for which we figured out the net force here, and that's of course up. Okay, so we've got two accelerations, and they both involve tension. The tension we've already discussed is the same. Neither one is completely solved, because they're both just expressed in terms of the unknown tension. But here's what we know. We know that those two accelerations have to be the same. Right? Why is this? Well, let me show you the picture again from early on. If this one goes down with a certain amount by 10 centimeters, this one has to come up 10 centimeters. If this one goes down by 10 centimeters per second, this one would have to come up by 10 centimeters per second. Right? If this one accelerates with a certain acceleration, this one has to have the same acceleration, because the length of the string does not change. Perhaps something could have said it explicitly, but it's a string, it's not a rubber band or something. Right? The length of the string does not change, and therefore the acceleration of this one down is the same as the acceleration of this one up. The speed of this one down is the same as the speed of this one up, and so on. So let's write this down. We connect them here, but also A heavy is equal to A light. There's just one acceleration. Of course, this one is down, this one is up. That's how we defined it. But these are just the magnitudes. Just call it A. Call it two words. Call it A. Right, so we just did two accelerations here for each one of each box, but they're the same. So we're just going to give it a single, as just one acceleration in the whole system. Let's call it A. Okay, so what can we write down then? We can write down you can write each of those just with A. A is mg minus T over M, and A is also equal to T minus mg over M with the little m's. So now we have got two equations, we've got two unknowns, so we can solve for them. Two equations, two unknowns. That implies we can solve. Our two equations are, of course, our two unknowns are, of course, A and T. How do I do this? Well, they're different. I mean, at this point, it's just algebra, right? But let's do the algebra. Maybe what I'll do is I'm going to first find the tension. So to find the tension, well, to eliminate A, I might just say, well, this is equal to A, this is equal to A, so those two are equal to each other. So we're going to find T, so I'm going to set mg minus T over M is T minus mg over little m. Alright. Okay, now we just have to rearrange this. A bit of a pain, but you know, part of doing physics. So I'm going to multiply everything by big M and by little m. I'm going to get mg minus mt is equal to mt minus mmg. Of course, when I say this, right, make sure you use the right m's in the right places, and make sure you follow each step of the algebra. Okay, let's take all the t's to one side, and all the rest to the other side. I'm going to get m. I'm going to take this one over here, becomes a plus, so I've got 2mmg, and that's equal to m plus mt. Right, so this went over there, this went over this way. Again, if you're confused, pause the video, make sure you can get from there to there, right? This is fairly straightforward algebra, but I'm going to go through it fairly fast. And then so I'm going to get, finally, I divide by this thing here. T is 2m divided by m plus m, and then still times g. You do a sanity check. Is it the right units? Well, it's going to be mass, kilogram, kilogram. So kilogram squared over kilogram, right? Adding kilograms to kilograms, still kilograms. So kilogram squared over kilograms times meters per second squared, the unit of G. Okay, that's kilogram meters per second squared. That's indeed newtons. That's the force. Okay, makes sense. So that's the tension in the string after we've let go, right? Of course, before we've let go, well, the tension is different left and right, and in each case, it just balances out the weight. But this is after we've let go. Let me just make a note. I know I've said it, but I know from past experience that tends to cause confusion when it comes up in an exam. Suddenly the tension before is the same as after. It is not. This is just the tension after the fact. Okay, I found the tension. I want to find the acceleration. Now what I could do is I could take this and plug it, say, into here or here, and then solve. I'm just going to go back to the starting point, go back to here, and solve for acceleration from there. Let me do that. I'm just going to write out the equations again. A is mg minus t over m, but I'm going to actually take the m to the other side. And similarly for this one here, I'm going to say ma is t minus mg. I'm just rewriting Newton's second law in the F net is ma form rather than a is F net over m. Same thing. Okay, so I'm going to eliminate t. So the way I'm going to do this, so what I could do is I could say, okay, t equals ma plus mg. Right, that'll work. I can rearrange this for t and plug in here. It's an option. I'm going to show you another little technique that I quite like. So let me just label those equations 1 and 2, and sometimes this technique is going to be useful, sometimes not. I'm just going to add equations 1 and 2. What it means, I'm going to add the left-hand side to left-hand side, the right-hand side to the right-hand side, right? If this is equal to this and this is equal to this, then this plus this is this plus this. That's all I'm doing. The left-hand side, I want to get ma plus little ma. The right-hand side of mg minus t plus t minus mg. Now you see why this is a fun little thing to do, because the t just drop out fairly straightforwardly. I can simplify this a little bit. Right, again, make sure you can go from one line to the next. So I get that a is m minus m over m plus mg. Now, of course, if you'd gone with the other way of, just rewriting one of the equations as t equals all the other stuff on the other side, you're going to get to the same answer, right? Mathematics is consistent. So we've got the acceleration here, and we found the tension up here, and so we're done with our problem. Now, let's look at this expression a little bit. So what it's telling us is the bigger the difference between the masses, right, the bigger the acceleration. If this is a lot bigger than this, well, then this number is going to be big. Whereas if this is only a little bit bigger than this, then this number up here is going to be small. And that intuitively makes sense. So it's another sanity check. We'd also check the units. Kilogram minus kilogram is kilograms on top, kilograms on the bottom. Okay, it cancels out. I'm just left with meters per second squared. Indeed, that's an acceleration. Okay, so we did some sanity checks there. That makes sense. So I'm going to find you another little way to find this, another sort of way to analyze the system. Let me just go back to my original picture again. Here. Another way I can treat this is by just looking not at the individual two weights as objects, but as looking at this whole thing as one object. Right, alternatively, an alternative way to analyze this. Right, alternatively, and let me write what we're doing. Look at system as a whole. So we looked at a system as two chunks, and for each one we drew a free body diagram. So it looks something like this. Right, here's a wheel, here's a wheel, here's a wheel. If I look at the forces on that system, then the tension isn't there. Right? The tension is internal to the system. Tension internal. It's happening inside the system. Right? It's holding the system together, but it doesn't itself act on the system. Right? So, for example, when I kick a ball, I might talk about the forces on the ball, but I don't worry about the elastic forces holding the ball together. Right? That's irrelevant because the internal is between different parts of the system. So here tension has that role too. If I look at this whole thing as one system, then tension is internal to it. So that means the only two forces acting are mg on this side and mg on that side. So really it's mg, little mg pulling it this way, and big mg pulling it this way. Right? And so the net force is going to be mg minus mg, because they pull in opposite direction. I mean, they both pull down on the point where they act, but on the system they pull, one pulls counterclockwise, one pulls clockwise. So that's the net force. And then the mass is just the total mass, right? Just the total mass of the system. Those are the parts that have to be accelerated. And so that implies that the acceleration is net force divided by mass, which comes to mg minus mg over m plus m, or m minus m over m plus mg, just rearranging it. That's of course the same answer we found up here. Right, it's a different way to analyze the system. The catch here is that we don't get a tension, right? Because the tension is internal. So if you do want a tension, we have to go via this route of looking at the individual components of the system. Okay, so I hope that the example was useful to go through. Showed you some techniques of how to think about it, how to do some algebra here. So hopefully you'll be able to apply this in your homework as well, and in the exams, and in life, where you might be tackling similar problems. Thanks for watching.